Hello, welcome to this video where I'm going to explain how to bound an improper integral. Now, you know that the integral gives you the area between the curve and the x-axis. And you remember we used these little boxes earlier on to prove the fundamental theorem of calculus. Well, we're going to use those boxes again, but this time to bound an improper integral. So suppose we have a decreasing function, like this one. Okay, it's decreasing, here it is, it goes down. And I'm going to calculate the area from 0 to infinity. Well, it's going to be this, right? This is going to be the integral from 0 to infinity of the function, right? Great. That's going to give me the area. And I know, we can prove it, but I know that's actually going to be finite. Well, rather than just actually calculating the integral, let me use the idea of the boxes to bound it. So here I have the following boxes, great. And I have to realize, well, these are too big. It's going to give me a bigger area, right? First thing. And the width of each of these boxes is 1. And what is the height? Well, the height is going to be, the first box is going to be f of 0. Second box is going to be f of 1. Third, f of 2, f of 3. So the area of each one of the boxes is 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2, and so forth to infinity. That's a summatory. That's the following summatory from 0 to infinity of f of k. Or I could just write it directly this way. I can also do it the other way around. I can also find smaller boxes. Again, this is going to be too small, so adding them all together is going to give me a smaller area. And the boxes have width 1, and the height is going to be f of 1, f of 2, f of 3. So again, I'm going to have the following expression. The idea is that this improper integral, this one is going to be smaller than this and bigger than this. So I end up with the following expression. And that's how bounding an improper integral works. Okay, so this worked for this decreasing function. Let's look what happens with an increasing. So let's look at this one. This one's increasing. This is what it looks like. So first thing to realize, this area is underneath the x-axis. So it's a negative area, okay? Now, this area here, these boxes here, are actually going to give me a smaller area than this one because it's going to be a bigger negative number. So I'm going to get a smaller area. And these ones are going to be f of 0 plus f of 1 plus f of 2. Here you go. These ones, on the other hand, are going to give me a bigger area. Why? Because it's going to be a smaller negative number. And this is going to be f of 1 plus f of 2 plus f of 3, etc. So again, here I'm going to have my bounds for the improper integral. Wonderful. So here are the general rules. This is what the general rules look like. If the function is increasing, then I can bound it. I can bound the improper integral with the sums of the function from a to infinity on the lower bound and from a plus 1 to infinity on the upper bound. If it's decreasing, then it's going to be the other way around. A plus 1 in the lower bound and a on the upper bound. Great. That's the rules. This is what you're going to use. This is ultimately the whole idea. Now let's use it. Let's use it actually for an integral. Now, suppose we have to set the bounds for this improper integral from 3 to infinity of minus, open brackets, 1 over e, all of it to the power of x dx. Great. So, okay, is it increasing or decreasing? Let's check out, just in case. Just check out the GDC. Okay, so it's increasing. Wonderful. So what is going to be my upper bounds and lower bounds? They're going to be determined by this rule. Great. There you go. You got it there. Wonderful. So let's set up the bounds then. Well, this is what it looks like. I just put, instead of f of k, I'm going to actually write the function and so forth. Let's calculate this one. Well, let's start with calculating this one here. Now, realize it's like a geometric series, right? The ratio is 1 over e. So again, I guess it's going to converge, right? Because the ratio is between 0 and 1, or I'd say between minus 1 and 1. It's going to converge. Wonderful. Great. Good news. How do I find out what it converges to? Well, first of all, I'm going to use my formula from the geometric series, from infinite geometric series. But what I'm going to put in that formula, I'm going to need the first term. So what is the first term? Well, the first term is simply when I put k equals 4. So it's going to be 1 over e to the power of 4. So here's my formula for the infinite sums. I put the negative number in front of it because this is this negative number. So I'm going to find out that it's going to be minus 1 over e to the power of 3 times e minus 1. The other one, this is this bound here. The other one is going to be something very similar. This is going to be this bound here. So finally, I found my bounds, and I can say that the improper integral is smaller than this thing and bigger than this thing. Great. So what's the point of doing this? What's the point of doing this? I mean, I could have just calculated the improper integral directly. 1 over e to the power of 3. Why do I need to do that? Is it really going to be that useful? Here's the answer. Maybe not so much. But what really is going to be important, rather than bounding the improper integral using a series, is going to be bounding a series using an improper integral. That is going to be very useful because, believe it or not, series are actually a very important and powerful tool in calculus. You're going to be looking at series pretty much from here on for quite some time. You're going to have power series, Maclaurin series, all sorts of convergence tests. And it's a very powerful tool. You're going to be able to do a lot of things that you couldn't do before using series. So we're going to be using this idea here mostly for understanding series. But nevertheless, let's again look at an example where I'm going to bound a series using an integral. Okay, let me bound this series here. Okay, so first of all, let's find out what the function is. Here's the function. So does the function have, is it decreasing or increasing? It's decreasing. So this is the formula I'm going to use. Now, let's actually first solve the integral, because I can solve that, right? And the integral, when I solve it, is going to be 1 over 16. Now, this is 1 over 16, which means that when I put it here, 1 over 16 is smaller than what I have to calculate. So I have a lower bound. I have a lower bound at 1 over 16, right? Now, how do I find an upper bound? How do I find an upper bound of this thing here? Well, what I'm going to do is I'm going to use the other side, this expression here, right? This is the other side. I know that this thing here is smaller than 1 over 16, right? Great. Now, but the problem is that I have this summatory starts at 5, this starts at 4, so that doesn't quite help me. Well, this is how I'm going to fix it. This is how I'm going to make this summatory start at 4. All I'm going to have to do is add at both sides of this inequality what would be the term with k equals 4, which is this thing here. I add it here, and I add it here. And now, well, this and plus this just becomes the summatory starting at 4. And I operate the other side, and I get 3 over 32. So I know that the summatory starting at 4 is smaller than 3 over 32. So that's how I get my upper bound. And finally, I end up with the result. Well, thank you very much for watching. That's all the improper integrals you're going to need for this course. So good luck with that, and see you next time with a lot of series. Goodbye.